All right, this is chapter 2, homework for Physics 201. Have a graph here showing the motion of a car stuck in stop-and-go freeway traffic. If you only knew how far the car had gone during this entire time period, what would you think its velocity was? Well, I would think that it would be like the average velocity, and that is the time that it traveled divided by the distance that it traveled. In this case, that would be delta x over delta t, which is, in this case, it said 90 meters, which is the distance that it travels. You can't see the full picture here, I'm sorry. 90 meters divided by the total time, which is 14 seconds. And you can't see the full picture, but you can see it in your book. And that gives you an average velocity of 6.4 meters per second. All right, but I want to know what is I also want to know what is the car's maximum velocity, and that's where it has the largest slope. I'm going to sort of draw this line up here. That line goes on up like that. As I said, you can see it in your book, but not here. What is the car's maximum velocity? And then we'll compare these two values. The maximum velocity is the velocity up at this point. Now this is distance versus time, and the slope of a distance versus time graph is equal to the velocity, or the instantaneous velocity. So I want to find the slope of this line right here, and the slope is rise over run. And if I look at this, I'll make a little triangle, and I can find the rise by looking over at the x-axis, or the y-axis, and the run by looking at the x-axis, and I find that it's 90 minus 60 is the rise, and that's in meters. I'm going to put an M there, divided by 1.2 seconds. That is the elapsed time for that leg, 1.2 seconds, and that gives me a speed of 25 meters per second. So you see that the speed there is actually quite a bit larger than the average speed, but the average speed is slow because, well, you have some places where you just stop completely and have zero velocity, so your average speed comes out quite a bit lower than your highest speed. It's possible to shoot an arrow to speed as high as 100 meters per second. Friction is neglected. How high would an arrow launched at this speed rise if shot straight up, and how long would the arrow be in the air? I always find it useful to draw a picture. Let's draw a picture right over here. This is my ground. I have an arrow. I shoot it up, and it comes right back down again. All right, and now I'm just going to write all the things that I know. First of all, I know the acceleration of the arrow is minus 9.8 meters per second squared. That's always true on the planet Earth. I know that the velocity up here at the top is equal to 0. The object goes up in the air, it stops, and then it starts coming back down again. I know that down here, I'm going to call this V0, it's 100 meters per second. That should be meters per second, because that's what it says in the problem. And I want to know what is this distance. So I'll just call it y. What is that distance y? So, how high would it go if it shot straight up in the air? I always like to write my equations. You only have two equations. That is v equals v0 plus at, and then y equals y0 plus v0t plus 1/2 at squared. I always like to just write these, and when you get your test, you can just write them up at the top of the test and just refer back to them when you're doing these kinematics problems. There are other equations that you can derive from these two equations, but these are the basic equations of kinematics, and we showed you in class how to derive them, and you'll be responsible for those derivations too, by the way. So I want to know how high it goes up. So that means I'm going to be looking for y. I'm going to get rid of my y0. It's 0 in this case. It often is. V0, I know that. A, I know that, but I don't know t. So in this second equation here, I don't know what y is, nor do I know what t is. So I need to figure out what t is before I can answer that question. So let's look at this one. I know what v is 0 up at the top. I know what v0 is, I know a, and I know t. So I'm going to start then answering part b. That is, how long would the arrow be in the air? All right, so v is equal to 0. excuse me, let me write out the equation first. V is equal to V naught plus AT. Now, V up at the top is 0. V naught is 100 meters per second plus A, which is minus 9.8, and then T. And this is the time to get from the bottom to the top. The bottom to the top. All right, I'm not going to make that distinction now. I'll just call it T. And then if I solve for T, I find that T is equal to 10 seconds. So I'm going to call this T up. That's the time for it to go from the top to the bottom, just to go up. Now, to go and answer part B, I want to know the total time. And the total time, that is for the arrow to get from here to here and then back down, is going to be 2 times 10 seconds, which is 20 seconds. It takes the same amount of time to go up as it does to come down, so it requires 20 seconds. But now I can also answer part A. Y is equal to V naught T. That's 1/2 AT squared. I can put in my values here. V naught is 100. T, that's the time to get from here to the top, is just 10 seconds, plus 1/2 of minus 9.8 times 10 seconds squared. I can look at my units here. Seconds cancel with seconds. Second squared cancel with second squared, and I'm left with meters throughout. That's, what's that, 1,000 minus 490. That's 510 meters. You can shoot at 510 meters, more than 5 football fields straight up in the air. This is a good example of a question. It's a two-step question. You have to figure out what is one variable in order to find the other variable. We'll see that in other problems as well. Drag racer starts their car from rest and accelerates at 10 meters per second squared for a distance of 400 meters. How long did it take the race car to travel this distance? Let's just write down what we know. I know that car starts from rest, so that means that V naught equals 0. Accelerates at 10 meters per second squared. All right, that's positive because she is speeding up in the positive direction, so her acceleration is positive. The distance, I'll call it x, it's 400 meters. And as usual, I'll say that x naught is 0, but we don't need to write that. And then how long did the race car take to travel this distance? I want to know what is t. And then I also want to know what is the speed. That is, what is v final, and I'll just call it v. All right, let's write my equations over here. V is equal to v naught plus at. X is equal to v naught t plus 1/2 at squared. All right, so let's see. Let's just look at this first equation. All right, I have v. That's what I want to know. I know what v naught is. I know what a is, but I don't know what t is. So I have two unknowns in that question. And then here, I know what x is. I know what v naught is, but I don't know what t is. And I know what a is. All right, so looks like I can take this equation. I'm going to go ahead and get rid of that because that's 0. I can say that x equals 1/2 at squared. Oh, but so I know x, I know a, but I don't know t. So I'm going to solve this for t, and that's part A. So I'm solving for part A. That's 400 meters equals 1/2 of a. That's going to be 5.00. It's a half of my acceleration times t squared. And I solved this for t. That's the square root of 400 over 5. I can look at my units here. I have meters, meters per second squared. So that's going to give me units of seconds. And I get 9 seconds. All right. And then I want to know what is the speed of the race car at the end of the run. Well, it's just v is equal to v naught plus at. V naught, as we said, is 0, so v is just equal to a times t. That's 10. times t. That's going to be 90 meters per second. 90 meters per second. That's about 200 miles an hour, just for reference. About 45 meters per second is about 100 miles an hour. Okay, so that's number 3. So the truck covers 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.8 meters per second. Find the truck's original speed, its acceleration. Now write a function of position versus time, taking its derivative and verify that speed is 2.8 meters per second. Da, da, da. What is the function of velocity versus time? Integrate and verify that the displacement is 40 meters. Okay, so for part A, I want to know the truck's original speed, but let's first just write down everything that I know. Actually, I'm going to write down my equations first. That is V equals V naught plus AT, X equals X naught plus V naught T plus 1/2 AT squared. All right, I'm going to say that X equals 40. X naught, as usual, we'll set equal to 0. T is equal to 8.5 seconds. The final speed, VF, equals 2.80 meters per second. And I want to know a couple of different things. I want to know the acceleration and V naught. So I want to know V naught. And then I also want to know the acceleration. Right? I want to know V naught and the acceleration. So I can start with these two equations. Both of these equations have two unknowns because both of them have V naught and both of them have acceleration in them. So what we're going to have to do is we'll solve this top equation for V naught, and I'll say that V naught, this is from the top equation, V naught equals V minus AT. And then we're going to take this and plug it in here for V naught. And then I can rewrite that second equation. X is equal to V minus AT times T plus 1/2 AT squared. Now in this equation, just double check, I should only have one unknown. I know X, I know V, which is VF, so this implied that that's VF. I don't know A, excuse me, but I do know T, and that's all. So the only unknown in this equation is A. So I want to solve this for A. So let's see what we can do here. We can expand this out. X equals VT minus AT squared plus 1/2 AT squared. So X is equal to VT minus 1/2 AT squared. And I am looking for A, so I'm going to solve this for A. So A is equal to VT minus, or excuse me, X minus VT divided by negative 1/2 T squared. And if I put in my values that I have for that, 40 minus 2.8 times 8.5, I'm going to write those out. 40 minus 2.8 times 8.5 divided by negative 1/2 8.5 squared. And that's equal to, keeping the proper number of sig figs, negative 0.445 meters per second squared. That's my acceleration, negative 0.445 meters per second squared. Forgive me, I got a little sloppy with my significant figures here, but that's keeping the appropriate number, negative 0.445 meters per second squared. Now that I know my acceleration, I can figure out what my V naught is fairly simply. because I already have an expression for V naught up here, and it's going to be V minus AT. So V is 2.8 minus a negative 0.445 times T, which is 8.50. And that gives me my V naught, and that comes out to be 6.58. And that's meters per second. So that's parts A and B, the acceleration and the initial speed. Now let's see, part C, write the function of position versus time. So I want to write the function of position versus time. I'm going to do that over here. Look, I already have it over here, right? So I'm just going to put in the values. X is equal to V naught T. V naught, I've already found to be 6.58 T. 6.58 T plus 1/2 AT squared. So it's going to be minus half of the acceleration I get 0.223. So that is my x as a function of t. And I just took it from this expression, putting in the coefficients for t and t squared. Now, I want to take the derivative. So dx dt, so this is going to equal v, by the way, is going to be 6.58 minus 0.445t. All right, I did 0.445 because I knew that I'd taken half of this value. All right, 6.58 minus 0.445t, that's my speed. And then I want to verify that the speed at t equal 8.5 seconds. So let t equal 8.5 seconds. Plug that in, I get 6.58 minus 0.445 times 8.5. Hopefully that'll get us the right answer. I haven't actually done this, so let's see. 6.58 and get 2.8. Is that right? Yeah, 2.8 meters per second. So that's my speed at 8.5 seconds, and notice that that lines up with what's in the problem. It's just sort of a different way of getting at the same number. And now I also want to write a function of the velocity versus time and integrate and verify that the displacement is 40 meters. So I can just come up here. This is my velocity versus time, and I can say that velocity equals v naught, which is what I found to be 6.58 plus at. That's negative 0.445 times t. Another thing I could do is I could, well, actually, let's see, I had that right here. I had my velocity function. Is I could take the derivative of the displacement function, which is there. All right, so now that's my velocity function. I want to integrate it, and I'm going to get the displacement. So remember, x is the integral of v dt. So I'm going to take the integral of v dt, 6.58t, minus 0.445 t squared over 2. And then if I put in my limits of integration, that's from 0 to 8.5 seconds. I'll get 6.58 times 8.5. I get 40 meters. All right, so that is part D right here. This is part C right here. You should be adept at using integrals and derivatives in order to get back and forth between position, velocity, and acceleration functions given a function. You'll see several more problems, and we've done several problems in class like that as well. All right, this graph represents the motion of a particle. The function describing this graph is this. Graphically determine the particle's instantaneous acceleration at t equal 1 seconds. All right, I had a typo here. It should be the acceleration, not the velocity, at t equal 1 seconds. Now, this is a velocity versus time graph. In order to find the instantaneous acceleration, I need to find the slope of this graph. If you're ever in doubt, just think about the units. So remember, slope is rise over run. And so if I look at the units of this, the rise would be meters per second over the run, which is in seconds. That's meters per second squared. So the slope of this graph gives me the acceleration. And you can use that for other things as well, like for the position versus time, that's x over t, or meters over seconds for rise over run. That's velocity. So I want to know the instantaneous acceleration at t equal 1 second. That is right here. You might want to use a ruler. I used a ruler in my notes. I'm just going to use a ruler to draw a line that's tangent, and then find a good triangle. I use this triangle, and I found the rise of this triangle to be, well, negative 10 to 10, so it's 20, and then the run to be 0.35 to 1.65, and there was a little bit of judgment call there as to, what is this on the x-axis, and so this total distance is, or total time is 1.3 seconds, and so the instantaneous acceleration is rise over run, that is 20 over 1.3, and 20 over 1.3 is 15 meters per second squared. And now you want to ask yourself the sign. This is a negative slope, so I'm going to do a negative right there. And you would have found that because the rise is actually a negative number because it's starting big and going small. But always don't worry about the signs until the end, and then just ask myself, was this a positive or a negative slope? Because it should be fairly obvious to you if it's positive or if it's negative. All right, so it's negative 15. Now for part B, I want to know the acceleration with calculus. All right, slope is derivative. So to find the acceleration, I just take the derivative of the velocity function. That is dv dt. And taking the derivative of this function, that's going to be 4t cubed minus 20t. And 9 doesn't change, so its derivative is 0. And I'm looking at 1 second, so that's 4 times 1 minus 20, which is negative 16 meters per second squared. I think that's pretty darn good because we did this sort of graphical method, which is not real accurate since we're just sort of estimating the slope there is 15, but the actual slope should be negative 16. So that's pretty darn good. What is the average velocity between t equals 0 and t equals 3.5 seconds? Okay, this should actually say what is the average acceleration. All right, the average acceleration equals delta v over delta t, and between 0 and 3.5, let me take this away, between 0 and 3.5, between here and here, my v final is going to be 35, so I'm saying this is 35, v initial is 10. All right, so it's going to be 35 minus 10 meters per second. And then my change in time is 3.5 minus 0 seconds. All right, so that's 25 over 3.5. That's 7.1 meters per second squared. Now remember, this is the average acceleration, so you need to make that change in your notes that it's acceleration, not velocity. All right, it's just what is the final minus the initial velocities over the elapsed time. We're not worried about what happens in between. We're only, for averages, we're only asking what happens at the beginning and at the end. I graphically determine the displacement of the particle between t equals 0 and 3.5 seconds. Now find this displacement with calculus. So if I want to find the displacement from a velocity versus time graph, I will find the area under the graph. If I want to find the displacement, I find the area under the graph. You have another page, so you can write on that if you like. But to find the area, I just make an estimate. So look, I'm going to say that these two together make 1 square. Those two together make 1 square. That if you were to flip this part over, you'd get 1 square. And then here, this is 1 square. This is 1 square. I will say that these two squares together make 1 square. And this one, I would say, is about a half a square. So we'll call this about half a... No, we'll call this 1 full square. So then we have 1 full square there. That's these, this, and this. All right? And then I'm looking also for... I'm going to say, let's see, this... And this is 1 square, and I'll call this a half a square. So here, I'm looking at 1.5 squares. All right, so what do I have? I had 1 square over here. I had 4 squares right here, and then 1.5 squares here. Now, each square corresponds to a certain area. So see, if I look at one of these squares, I have 10 on this side, 0.5 on this side. So 1 square is equal to 10 times 0.5, which is 5 meters. So an area under the graph of 1 square means that your object has traveled for 5 meters. 5 meters. All right, so I have 1 square on top, 1.5, 2.5 squares on top, and 4 squares on the bottom. Now, if the squares are on the top, if they're above in the positive velocity, that means it's a positive displacement. If it's below the x-axis, that means it's a negative displacement. So I'm going to say that I have 1, I'm just adding up the number of squares, plus 1.5 minus 4 times the area for 1 square, which is 5. And that should give me my displacement. That's 2.5 minus 4. 2.5 minus 4, which is what? Minus 1.5 times 5. So I get negative 7.5 meters. Negative 7.5 meters. All right? That's very rough. I just sort of estimated what is the area under that graph. Now I also want to find what is the displacement with calculus. And to find the displacement with calculus, I say that x is equal to the integral of v dt. I already have a function for v, so x is equal to the integral of t to the 4th minus 10t squared plus 9. And that is going to be t to the 5th over 5 minus 10t cubed over 3 plus 9t. And then I want to integrate that from 0 to 3.5. That's my limits for the time. If I put in those limits, I find that it's plus 2 meters. All right, so we were a little bit off in estimating what is the area under that graph, but the actual displacement is plus 2 meters, but I get a minus 7.5 graphically. But again, this graphical is very subject to problems, and we're just sort of estimating what is the area. Let me recap about graphically finding the displacement. Let's recap a little bit. If I have a function of v versus t, and it looks like that, and I want to know the displacement, I find the area under that graph and under that graph, and I add them together. And then I subtract the area above that line. And that's how I find the displacement. I add these two, and I subtract this one. We'll do this in class too, so you'll get more experience with it. But it's a good test question, okay? Dealing both with graphical analysis and also with the calculus analysis. All right, find the instantaneous velocities of the tennis player on this figure at 2, 5, 7, and 11 seconds. 2, 5, 7, and 11 seconds. This is position versus time. So to find velocity, I just take the slope. So let's first look at 2 seconds. That's right here. I want to know the slope of this line. All right, my run is 4. My rise is 20. So it's 20 over 4, which is 5 meters per second. For B, at 5 seconds, that's right here. All right, the slope of that line is obviously 0, so 0 meters per second, because there's 0 rise. For C, at 7 seconds, that's right here. I want to know what is the slope of this line. Okay, so I did my rise over run. I had my rise is obviously 40 minus 20. That's 40 minus 20. That's in meters. Divided by my run, and you might have slightly different numbers here, but I thought it was 9.8 minus 6. That's 9.8 minus 6. It's in seconds, and I get 5.3. All right, and then finally at 11 seconds, that's right here. I want to know this slope. All right, my rise is the same, sort of. It's 20 minus 40 meters. All right, 20 minus 40. Notice that my final is 20, so that's why I switched them. Final minus initial position. And then the time, I said 12 minus 9.8. Again, you might have a slightly different value for that 9.8, depending on how you interpolate it. And I get minus 9.1 meters per second. So those are my answers. Those last two might be slightly different, but they shouldn't be terribly different from this. All right, the following graph describes the motion of a particle. What is the acceleration between 0 and 30 seconds? What is the acceleration between 0 and 30 seconds? Between 30 and 40 seconds, what distance does the particle travel? And how far away from the starting point is the particle at 55 seconds? All right, so this is velocity versus time. For part A, to find the acceleration, I need to find the slope. So for part A, I need to find the slope between 0 and 30 seconds. Between here and here. That is, what is the slope of this line? All right, and the slope is 0. You could also say, what is the average acceleration between 0 and 30? All right, and that would also be 0. That is, what is delta V over delta T? And that's also equal to 0. It's the same thing. All right. Now in part B, I want to know between 30 and 40 seconds, what is the particle's acceleration between 30 and 40 seconds. So again, I want to know what is delta V over delta T between 30 and 40 seconds. I want to know the slope of this line, the slope between those 2 points. And let's see, I get negative 40 as my final, minus 0. This is in meters per second. That is negative 40 minus 0, which is implied right there, divided by my time, which is 40 minus 30 seconds. That's 40 minus 30. And that gives me negative 40 over 10, which is negative 4 meters per second squared. Remember, in a V versus T graph, velocity versus time, acceleration is slope. Acceleration is slope. Now, what distance does the particle travel between t equals 0 and 30 seconds? That should say C right there. To find distance, you want to find the area. What distance does a particle travel between 0 and 30 seconds? The distance it travels between here and here. So I want to know what is the area under this graph right here. Do like I did before. I noticed that each square 1 square here is equal to 20 times 5. So 1 square is 100 meters. 1 square is 100 meters. How many total squares are there? I'm going to count them off here. Let's see, I'm just going to start with the obvious ones. 1, 2 squares, 3 squares, 4 squares. We'll call this a whole one. 5, 6. I'm going to call this one and this one my 7th square. I have 8, 9. I'll include that little bit with the 9th one. And then 10, which I'll also include this remainder with that one. So I got 10 squares there. And again, that's a bit of an estimate. Oh, I missed one. We'll call this a half. So I have 10.5 squares. If each square is 100 meters, that means that I have 1,050 meters. All right, so that's the area. Now for part C, how far does it travel from the starting point? How far away from the starting point is the particle at 55 seconds? So now I want to know the area above this line. And I'm going to subtract that distance from what I got in part C in order to find the total distance that it traveled. So I'm going to do like I did before. I have 1 square, 2 squares. We'll call this one 3, but we'll include this little bit. We'll call this one 4, including that little bit, and then this is another 0.5. So on that second part, I got 4.5 squares. If each is 100, that means it's 450 meters. So the total distance traveled is 1050 minus 450, which is what, 600 meters. Your answer might have been slightly different based on how you added up the area, but it should be pretty close to 600 meters. All right, you're looking into a deep well. It is dark, and you cannot see the bottom. You want to find out how deep it is, so you drop a rock in and you hear a splash 3 seconds later. How deep is the well? And then gives you the speed of sound in air is 343 meters per second. All right. So let's start just by writing my equations. It's not a terribly easy problem, so bear with me. But you might have a problem like this that is a 2-stage problem where you have an object traveling in 2 different paths at 2 different speeds or accelerations. So start by writing everything that we know. Actually, first let's write the equations. I have V equals V naught T. Excuse me. V equals V naught plus AT. V equals V naught plus AT. And then Y equals Y naught plus V naught T. It's 1/2 AT squared. So those are my 2 equations. I know that the total time is 3 seconds. All right, I know that the velocity for sound is 343 meters per second. I know that the acceleration of the rock is equal to minus 9.8 meters per second squared. The acceleration of sound is 0 meters per second squared. It travels at a constant speed. I also know the initial velocity of the rock is equal to 0. All right. The velocity of the sound, on the other hand, is equal to its initial velocity of the sound is equal to its final velocity of the sound. That comes, by the way, from this equation, that if acceleration is 0, the final equals the initial velocity. All right, so that's what I know. I'd like to draw a little picture to help us think about it. Here's our well. I have a rock. It drops down into the well, down to the bottom. and then sound travels back up when you hear it. All right? There are two distinct times that I have in this problem. The time for the rock to drop, and then the time for the sound to travel. And those distinct times add up to give us 3 seconds. All right, so I need to develop an expression for that total time. So, write what I just said. That is that the total time, which we know to be 3 seconds, is equal to the time for the rock plus the time for the sound. Now, let's write expressions for time for the sound and time for the rock, and then we'll solve that equation. Let's do the sound first because it's easiest. Time for the sound. I know that y. Well, let's actually draw these. Let me label my coordinate system here first. So I have y naught for the rock. I'm going to call that 0. All right, and this is going to equal y final for the sound. And down here at the bottom, I have y final for the rock, and that's going to equal y initial for the sound, because that's where the sound initially starts. All right, so down at the bottom, I have the final position for the rock and the initial position for the sound, and at the top, I have the initial position for the rock and the final position for the sound. All right. So here I have y final for the rock, y final for the sound is equal to y initial for the sound plus v naught sound times t plus 1/2 a sound ts squared. I know that a is 0, so I'll just go that goes away. I also know that yfs, which is right here, is equal to 0. All right, so I have 0 equals y initial for the sound. That's at the bottom of the well, plus v naught s, which is just vs, times t for the sound. All right, so I can solve this then for ts. I get ts is equal to negative y naught s divided by vs. You have to be careful with your signs in this case because you just have to make sure that you're using the same coordinate system. The signs can get a little mixed up, so just be very careful with your signs. All right, now let's do t for the rock. All right, so I have y final for the rock. This is coming from this equation, equals y initial for the rock plus v naught r, the initial speed for the rock, times t plus 1/2 ar pr squared. V naught I already know is 0. I also know that y naught for the rock is 0, so that simplifies that expression, and I can solve for tr. So tr is equal to the root of 2 times y fr, that's final for the rock, divided by ar. All right, so now I have these two expressions for the time for the sound and the time for the rock. I can put them together and solve for y. Put them together and solve for y. All right, see, I know that this plus this equals 3 seconds. All right, I know what vs is, I know what ar is, and further, I know that yfr is equal to y naught s. So I'm going to make that simplification here. Yfr is equal to y naught s, and just to make it simpler, I'm just going to call that y. So that's going to be the depth of my well. And you need to recognize that this number should come out in the end as negative, because if I have up top be 0, that means down at the bottom has to be negative, because it's in a negative. In this coordinate system where down is negative. All right, so YFR equals Y naught S, and I'm just going to call it as Y. And then I can come back to our original expression, T equals TS plus TR, because I know that those two have to add up to 3 seconds. And so T is equal to negative Y over VS plus 2Y over A, root 2Y over A. And I'm just assuming that A is AR because that's the only acceleration we have. All right. I can go ahead and put in some numbers here. 3.0 equals negative Y over 343 plus 2Y over minus 9.8, leaving out all the units just to make it easier to write. Now notice that I have a negative under this radical, which you can't take the negative, or that has a complex number, the square root of a negative number. But I've already said that Y has to be negative, so that square root is going to be of a positive number in the end because Y is negative. Now, to solve this, you might solve this in different ways. I'm going to do it this way. I'm going to say, I'll do it over here on the side. 3.0 plus Y over 343. That's equal to square root of 2Y over 9.8, negative 9.8. I'm going to square both sides. If I square both sides, it comes out like this. I get 9 plus 2 times 3Y over 343 plus Y over 343 squared. And that's equal to negative 2Y over 9.8. All right. This is a quadratic equation. You can use the quadratic formula to solve this. I put it in the ax squared plus bx plus c equals 0. Put it in that form. I'm not going to do that for you, but the numbers that you get for a, b, and c are a equals 8.5 times 10 to the minus 6. B equals 0.22. And C equals 9. And then we can find Y, in this case, is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. That's a quadratic equation. If you need to use the quadratic, I will give you that. But usually, I'm not going to require you to use the quadratic. I'll let you know in the class if that's to be the case. All right, but if I solve this for x, I get two answers. These are my roots of this quadratic equation, and that is that y is equal to negative 26,170 meters or negative 41 meters. Right, obviously, this is pretty ridiculous, so our answer is negative 41 meters. All right, negative 41 meters. Now you can take this and plug it back into some of our previous expressions. That is, we could plug it in here and find our time, and here and find our time, and then add up those times just to make sure that they add up to 3, and they do add up to 3. All right, that's a difficult problem, but not unreasonable for a test, though I probably wouldn't have you do the quadratic equation. Probably try to have the math work out just a little bit easier for you. But make sure that you're capable and able to work with these types of problems where you have the motion changing, that is maybe going from accelerating to not accelerating at some point during the motion. We can work some other problems like that in class. Okay. This photo shows John Young jumping on the moon and saluting at the top of his jump. The video footage of the jump shows him staying aloft for 1.45 seconds. Gravity on the moon is 1/6 as strong as the Earth. Compute the height of the jump. Let's just write down what we know. I know that my acceleration on the moon is minus 9.8 over 6. 1/6 of that on the Earth. That's minus 1.6 meters per second squared. I know that the total time in the air is 1.45 seconds. I want to know what is the height of the jump. I'm going to say that y naught equals 0. And I also know that the time in order to get to the top, let's do a little sketch here. He goes up and he comes back down again. All right, the time to get from here to here is half the total time. So I'm going to call that t top is 1.45 seconds over 2. That is 0.725 seconds. All right, so the time to get up to the top is 0.725 seconds. Now, I also know that up at the top that my final velocity is equal to 0. So I can, I'm going to write down my equations. V equals V naught plus AT. Y equals V naught T plus 1/2 AT squared. That's assuming that Y naught is 0, which it is in this case. Well, let's see, what am I looking for? I'm looking for the height of the jump. So I'm going to be looking for Y here. But I don't know what V naught is. And I don't know what Y is. So I have two unknowns in that equation, V naught and Y. So I can start with this top equation. Watch what I do here. I'm going to solve that top equation for V naught. V naught is equal to V minus AT. I just solved this equation here for V naught. And then I'm going to take this, I'm going to plug it in right here. All right, so I get Y equals V minus AT times T plus 1/2 AT squared. All right, now at the top of the trajectory, V is equal to 0. So I'm going to make that 0. All right, that's from here, the top of the trajectory. And so I can, Y equals negative 1/2 AT squared. Negative 1/2 AT squared. I can put in my values here. Negative 1/2, negative 1.6. And then the time to get the top of the trajectory is 0.725 seconds. That's squared. And that gives me a value of 0.42 meters. All right, just double check that. That doesn't seem right. 0.5. Yeah, 0.42 meters. 0.42 meters. So about a half a meter he jumped up. All right. So that's the answer. A model rocket is launched straight upward. Its altitude y as a function of time is given by this function, where b is 82, c is 4.9. Use differentiation to find a general expression for the rocket's velocity as a function of time. Okay, well, velocity is equal to dy dt by definition. All right, y is given bt minus ct squared. The derivative of that with respect to t is going to be b minus 2ct. b minus 2ct. If I put in my values, that is 82 minus 2 times 4.9, which is 9.8 t. I said 2 times c here, which is 4.9. All right, so that's my expression for v using calculus differentiation. That's part A. Part B, when is the velocity 0? Well, I can just say that the velocity equals 0 equals to 82 minus 9.8 t. And I just solve for t. And that'll tell me the time when the velocity equals 0. So that time is negative 82 over negative 9.8. And that's equal to 8.4 seconds. And then that's it. Let's ask another question though. When is the acceleration 0? When is the acceleration 0? Or rather, what is the acceleration at this time? So what is at t equal 8.4 seconds? All right, it comes to a rest, so does that mean that the acceleration is 0? That's really what I'm getting at. So this isn't in the question, but you should know how to do this. You know how to do this regardless. So I have a velocity. I know my acceleration is the derivative with respect to time, so it's going to be minus 9.8. Because the derivative of 82 is 0, the derivative of minus 9.8t is just minus 9.8. So the answer is that the acceleration is minus 9.8 meters per second squared. Even though the velocity is 0, the acceleration is still minus 9.8 meters per second squared. That's the end of chapter 2.